I'm getting this. It says it's recording. Okay, okay. So if you want to calculate the average rate of change of a function, first of all, what does that even mean, right? Like, what does that look like on the graph? Well, on the graph, as we've talked about before, if you have a function, let's say that that's a function, cool? That's y equals f of x. Notice that at different points on the curve, the steepness is different. Here, it's kind of going in a negative direction, and it's not very steep. It's kind of flat. Here, it's getting more and more steep as you go up. Now it kind of flattens. It goes down a little, comes up, and so on. Like the curve, it's not just a straight line in this case. It's like a wiggly curve. Cool? Okay. So the rate of change of the function in general, like we've talked about before, I'm going to just abbreviate it this way, just for the sake of my board being super tiny. The rate of change of the function, not the average rate of change, but the instantaneous rate of change. And BTW, instantaneous means at every point on the curve. Or rather, hold on, at each point on the curve. That's what we're talking about by instantaneous. We're saying, well, how steep is it right there, or right there, or right there, or right there? Cool? Now, we can't solve that using pre-calculus mathematics. We need to use calculus to solve that. We need the theory of limits. We need this extra idea of things moving towards a number without getting there to be able to handle this. But for right now, what we can find is the average rate of change. This is a pre-calculus type quantity. Okay, hang on, I've got my eraser here. Cool? Okay, so the average rate of change, so the instantaneous rate of change, BTW, is going to be exactly equal to the slope of the tangent line. Remember, the tangent line is a line that rests on the curve at a single point. It doesn't cut through the curve. And there's only one line that exists that'll do that. Any other angle you balance the line like a seesaw, it's going to cut through that curve a little bit. Cool? So there's only one line that will exactly touch the curve, exactly one point. And so the slope of the tangent line at that point that slope, that is exactly equal to the average rate, that is exactly equal to the instantaneous rate of change of the function. The question is, how do you find that slope, right? How do you find that slope? Because you only know one point. You only know that one point. Remember, the formula for slope in geometry, that is rise over run, is specifically given by the difference between two y values, that's the rise, over the difference between two x values, that's the run. And what are those x values and those y values? Well, that's because you have some point, x1, y1, some other point, x2, y2, on the xy plane, and you draw a line between them. And then you calculate the slope here, right? You'll remember that from geometry and stuff. Cool? So you take those numbers, the y coordinates, take their difference, subtract them, do the same with the x coordinates, take the ratio, the fraction, and you get the slope. I know you know this, but what I'm trying to point out is that here we don't have 2 points. This formula to calculate slope requires 2 points. You have to have 2 points. It doesn't make any sense. With 1 point, how can you possibly calculate the slope with 1 point? I mean, look, here's 1 point, and like, here's 2 totally different lines going through it, right? Those are like totally different lines with different slopes. So like 1 point is not adequate to calculate a line. A line is defined by 2 points that it passes through. Cool? So now I'm just going to tell you, so you don't feel all bleak and hopeless about it, that we can find that. It's a really, really big deal in human thought, in the history of humans, being able to find the instantaneous rate of change. And we're not doing it right now. We will, though. soon. The average rate of change is going to be equal to, as you'll remember from a previous lecture, it's going to be the average rate of change is equal to the slope of a secant line. A secant line is a line that connects 2 points on a curve or shape. Cool? See how I got rid of the tangent line and I replaced it with a secant line that's nearby? You can kind of see how those two lines are similar. They have similar slopes. I mean, I just made all of this up and drew it by hand. It's not very accurate. You can kind of see that. Cool? All right. So in any event, this is just finding the average rate of change. What I'm telling you is the average rate of change is the slope of that secant line. And what is that secant line doing? Well, here you have x2. Here you have x1. You have some y value. So this point on the curve is y2. Sorry, it's x2, y2. This point down here that the secant line's cutting through is x1, y1, this point. And the slope, the average, I'm going to just abbreviate everything, rate of change in this case, is equal to the slope of the secant line, which is equal to y2 minus y1 over x2 minus x1. Sorry for my bad handwriting. I almost failed 4th grade because I failed to learn how to write adequately, like with good handwriting. But my teacher let me slide through. Probably shouldn't have. Okay, so, but what is y2? Well, that's just y is just f of x. So y2 is the f of x value that's above x2, right? You go from x2 up to y2. So y2 is f of x2. And what does that mean? You just plug in the value x2, whatever that x value is, into your formula. Then you subtract y1, right? You subtract this x, the y value, which is the function evaluated at that x value. And then all of that is over x2 minus x1. So here we've rewritten the slope formula just by writing everything in terms of the x variable. We got rid of those y variables and instead wrote f of x using the x variables. Cool? But the slope formula from geometry, I hope that this is convincing, that that slope formula exactly gives you the slope of this secant line. Does everybody see that reasonably well? Okay, so the average rate of change, let's just do a problem really fast. Okay, well, here, I'm going to give you a couple of really quick definitions. If f of x is a function, let's say y equals f of x is a function that tells you how far you've gone. Let's say, let's replace x with a variable t. Look, x and t, these are the two most common variables in calculus. X usually implies distance or location. A location is x. That's a place on the number line. T usually implies that your number line now represents time. Cool? So does your variable want to represent a place, a location, or do you want it to represent a span of time? So as time is going, your function is changing. It's a little different feeling. So but it's the same thing. All I'm saying is we have our graph and now we have a t-axis and a y-axis. And so let's take a function of time like that. Actually, let's make a specific function. Let's make it be y equals t squared. Notice again, I've just replaced x with t. And I have bad handwriting and It didn't erase that completely. So y is a function of time. It's t squared equals t squared. T squared is an upward facing parabola. It's opening upward, and it's centered here. It's a vertex. It's vertex. That's what you call the bottommost or topmost point, is centered on the origin, the point 0, 0 in the ty plane. I'm changing variables to mix them up because you see these in your problems already. So I don't want to stick to x all the time. So this is a function. Now, if f of t represents the distance traveled in a time interval t, like you go to Atlanta and it takes you 90 minutes. So t would be 90 minutes. And the distance is whatever, 60 miles or whatever. Cool. So if f of t, for instance, is the distance traveled in time t, I know that's about what, actually Atlanta is more like 2 hours in the morning and the evening because I lived there. I just moved to Athens recently. And I used to commute every day to UGA. Okay, so in any event, so the distance traveled in time, then the average rate of change of f of t represents the speed or velocity. I'm just telling you this. This is kind of a definition-y kind of deal because because if you want to calculate speed, you take the average rate of change of your distance, right? Like if you're driving in your car at 60 miles an hour, what does that mean? That means that in 1 hour you've traveled 60 miles. Now, does that mean that you went 60 miles all the time? No, you might have like been going faster because the speed limit might be faster. You might have stopped for a while, so you're going 0 sometimes. But on the average, you went 60 miles in an hour. So that means that your average speed was 60 miles an hour. Anyway, so let's work this problem. I'm just telling you that the interpretation is the average rate of change would be the speed or the distance. I mean, the speed or the velocity. Okay. So now let's find the average rate of change of this function on the interval. And when we talk about intervals, we usually mean on the x-axis. And let's go for the interval 0 to 1. Okay. Well, the average rate of change from the previous formula is going to be f of x2 minus f of x1 over x2 minus x1. Cool? And notice that this is x1 and this is x2. That's the interval we're trying to find the average rate of change on. The endpoints of that interval are the points we're going to use as our x values. Cool? Oh my gosh, you're probably thinking in your mind, teach, it's not an x-axis, it's a t-axis. Sorry about that, students. It's a t-axis. So we just change all of those variables to t's. Sorry about that. There we go. Okay, so that's T1, that's T2. So we're gonna do, look, these are the steps to do this. You just take, you write down f of T2, that's gonna be 1, f of 1, minus f of T1, that's 0, over T2, that's 1, minus T1, that's 0. That goes down kind of nicely. Okay, well, what is f of 1? F of t is t squared. So f of 1 is 1 squared minus f of 0. F of 0 is 0 squared. And that, again, is still over 1 minus 0. Well, this is just 1 minus 0 is 1 over 1, aka just straight up 1. It turned out the average rate of change from 0 to t equals 1, which is the line that connects, the slope of the line that connects these 2 points, the secant line. Oh my gosh, my drawing's terrible here. I just decimated my previously nice drawing. But anyway, the slope of that line, and you can kind of see that, because that line is connecting 2 edges of a 1 by 1 square. Anyway, it's kind of believable even from my junky drawing. So that's a computation that finds the average rate of change. Now, the average rate of change and limits in general have one case that's really important in this class, and that's called the difference quotient. The difference quotient of a function f of x is the average rate of change on the interval, is the average rate of change of f of x, or of f of t, let's say, on the interval a to t. Sorry, let's make that second one x. So that's t1, and that's t2. AKA f of t2 minus f of t1, in this case, over t2 minus t1, the average rate of change. I'm just going to go ahead and change these. No, I'll go ahead and change them as I write. Well, that's f of x minus f of a. See, this is the left and the right-hand point of this little interval over x minus a. And what does this represent? It represents, if we have a function, this is the point A, and this is the point t equals x, that's t1, that's t2. Well, then this is y1, and it's going to be f of t1, which is f of a. Sorry about my junky handwriting. Let's see if I can get that a little better. And this point here is going to be f, y2 is f of t2, which is x. We're going to connect them to get the secant line. Oh my gosh, let's see if I can do this reasonably okay. We're going to find the slope of that secant line, and that's what we got right there. That, in this setup, where the left-hand point is a and the right-hand point is called x, and you draw a line to connect the 2 points on the function, you can see that kind of gives you, it kind of looks like the average steepness of the function. So now, what if, oh, and by the way, the difference quotient, f of x minus f of a over x minus a, difference quotient, it's kind of a technical sounding word, but it's really pretty simple. It's a difference. Difference means subtraction. See, you've got subtraction upstairs and downstairs. And it's a quotient. Quotient means like a fraction or division. See, we're dividing 2 differences. It's a difference quotient. Cool. Okay. Now the difference quotient the deal is that you have your point A, you have your point X, you have your function, that's f of x, that's f of a, the y values. If you let x slide towards a, as x moves towards a, like let's say it goes to this point, well, this little like point here, imagine that's like a roller coaster car. As x slides along, it drags the car along with it down the curve. So it goes to there. And as x keeps sliding towards the point A, this little roller coaster car keeps sliding towards f of a. You buy that? Right? If x is moving that way towards the point A, then the little roller coaster car up here that's attached to x, it's being dragged along with it, the function's value, sliding down the hill towards f of a, hopefully. You all buy that? That is the limit as x approaches a from the right-hand side in this case, in this drawing, of the difference quotient the slope that passes through these lines is going to get really, 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 really close to the slope of the tangent line that I can't actually draw here very well, but is going to equal the instantaneous rate of change, aka the slope of the tangent line at that point at x equals a. I'm just saying, the secant line slope, as it's getting closer and closer and closer to that point, is going to get really close to the slope of the tangent line that just rests on that point. I'm going to come back to this, but I want you to see how these calculations are going down while you're starting to do them, okay? Okay, that is the end of my mini lecture on the difference quotient and on the average rate of change versus the instantaneous rate of change. Cool?